Everybody, let's look at this one here with this rocket engine. It says the model rocket is launched vertically at time t equals 0. The rocket engine provides a constant acceleration for 3 seconds and then stops firing and is in free fall. So for 3 seconds, the engine's firing, then shuts off, it's in free fall. The vertical velocity is a function of time. For the first 5 seconds of flight as shown below, take up to be positive there. Okay, so first thing that they want us to do here is they say from the graph, well, they don't say from the graph, but you should know to do it from the graph, calculate the maximum height reached by the rocket. So on height, by the way, is a delta y, a displacement, and on a velocity versus time graph, then the area under the curve is what is going to give us a displacement there. So first off, we need to do area. Second off, we need to make sure we know where to calculate this area. And the maximum height is going to be the peak, and the peak is when we reach a velocity of 0. So we want to do it from here all the way to here. Sometimes people make the mistake where they stop at 3 because they see this peak and they think that's the peak, but that's when the engine shut off. So it continued to rise for another second there. So just find this area right here. And so that area is going to be 1/2 base times height, which is 1/2. Our base is 4 seconds. Our height is 10 meters per second. And so we're going to get 20 meters is the displacement under there. And so that's our maximum height. All right. So next part, it says calculate the time at which the rocket hits the Earth after being launched. Now, one thing you have to be careful of here is you cannot solve this problem in one swoop because we've got two different accelerations here because I got 2 different slopes. And so you cannot use the kinematic equations in just one case here because the acceleration changed in that means we can't do it at just one step. We got to do it at least in 2 steps. There's a lot of different ways you can do this one, but the way I think about it is if I look back to here when I'm at the peak and we already figured out that I'm 20 meters high, that means I need to fall 20 meters to get back to the base there. I know, or the ground, I know my initial y velocity is 0 meters per second at the peak. I know my acceleration vertically is in negative 10 meters per second squared because I'm already in free fall. And also on top of this, I know that we've already had 4 seconds pass in order to get to the peak. So I'm going to use this to figure out the time to hit the ground from here and then add that on to 4 seconds. And so this is the third equation that we see so often and is very useful when our initial velocity is 0 in the y direction. There is no initial y velocity, so that's 0. So we rearrange this equation to solve for our time. And then we plug in here, our time is equal to 2 times negative 20 meters as our displacement over negative 10 meters per second squared, and we will get 2 seconds. 2 seconds to fall from the peak, added on to those 4 seconds there, so 6 seconds is the total time. Then the last part here, they want us to graph a vertical position versus time graph based upon what we saw. And so we know that we're going to have curves here because we were accelerating. Position versus time graphs have curve when we're accelerating. We know that we're going to have one type of curve up to 3 seconds when we shut the engine off, and then another type of curve, let's just say that's 6 seconds right there. So in the beginning, while the rocket is firing, we are accelerating upwards. So we should have a positive, a smiley face curve right there. Then when we shut the rocket off, we're in free fall, we continue to rise for a little bit. So we do something like that, where we now have a frowny face, a negative acceleration. And so we rise a little bit more to the peak, but we still continue in free fall, the same negative acceleration down to the ground there.